Okay. So the features of the normal distribution. It says the frequencies start low, then increase to one or two high frequencies, and then decrease to a low frequency. So that's one characteristic. And the other is that the distribution is approximately symmetric, with frequencies preceding the maximum being roughly a mirror image of those that follow. And so I think yesterday I put some graphs on the board, but so normal distribution is bell-shaped. So it should look something like that. Of course, if we have bar graphs, it's not going to be a smooth curve, but like if you were to join, put points in the middle of each bar and join them with a curve, it would look like a bell. So we could have a graph where the frequencies start low, increase to a max, and then like slowly decrease to small frequencies again. But this one is not symmetric. It's like if you look at the high point, the right half is not a mirror image of the left half. So this fails the criteria 2. It passes criteria 1. They start low, increase to 1 or 2 high, and then decrease to a low, but it's not symmetric. Table 2.6, so below, satisfies these two conditions. The frequencies start low, so it starts at 1, increase to a maximum of 56, then decrease to a low frequency again. Also, the frequencies of 1 and 10 that precede the maximum are a mirror image of the 10 and 1 that follow. And it doesn't have to be an exact mirror image. Like if you had 1 and 10 and then 9 and 2, that's still pretty close, right? And usually they're going to be asking if it's roughly symmetric. So it doesn't have to be exactly perfect, but close. Okay, so here we have 3 tables, and it says, do any of the following tables seem to imply that the data follow a normal distribution? So what about this table 2.4? Does it satisfy criteria 1?
Yeah.
Yeah, they start low, they increase to 1 or 2 high, and then it goes low again. What about criteria 2? No, because these are not even close to mirror images of one another. 44.9 is the high point. The 1.3 and the 2.6, relatively close, but the 9 and the 42.3 are not even close. So no, this fails criteria 2. What about table 2.7? No, it doesn't even start low, right? It starts at the highest value. So this one, it fails criteria 1. And what about table 2.8? No. Also no. Because it doesn't start low again. It starts at one of the highest values. Did we have a table on the previous? Actually, if we go 2 back, maybe all the way to the first page. Would the one that we created fit a normal distribution? No, because again, it starts high, right? So this one also doesn't. So you want it to start low, go high, and then go low again and have approximate symmetry.
Like on table 2.8, there's a gap in the middle.
Right.
Is there a term for that?
It is called bimodal. So it would have, and we'll talk more about the mode in section 3.2. The mode is the one that occurs most frequently, and actually this one is the one that occurs most frequently. But if you look at a bar, like a bar graph of this, it would have 2 high bars, and then nothing, and then a low bar, a high bar, and then kind of a medium bar. So yeah, there are like kind of 2 separate high points. Yeah, so that's called bimodal. Okay, so example 4, exploring data. What does a gap tell us? Like if we have this gap in a table. So table 2.8 is a frequency distribution of the weights in grams of randomly selected pennies. Examination of the frequencies reveals a large gap between the lightest pennies and the heaviest pennies. This suggests that we have two different populations. So there's one group that's completely different from another group. And then some information that would help explain this is that pennies made before 1983 are 95% copper and 5% zinc, but pennies made after 1983 are 2.5% copper and 97.5% zinc. So they almost totally switched the makeup. And so obviously the zinc, these are a little bit heavier, right? The 25 is the most common. And then the older ones, oh well, I guess one of them is heavier. Actually, I think copper is heavier than zinc, but I think you'd have to look at the periodic table. But yeah, so one of these groups is the one that's primarily copper, and the other one is the group that's primarily zinc. Okay, so say we were given this problem, and this is from the book, number 8, on page 61. Again, this is of the ebook. So years the president lived after their first inauguration. So there were 8 presidents who only lived 0 to 4 years after their first inauguration, 2 presidents who lived 5 to 9 years, and so on. So the first thing, suppose we were going to make like a histogram of this data. What's the class width here? 5, right? And you can look at either how the lower endpoints increase or how the upper endpoints increase. So if you look at the lower, 0, 5, 10, 15, 20, they go up by 5 each time. So do the upper endpoints. 4 to 9 is 5, 9 to 14 is 5, and so on. So the class width is 5. And so on Tuesday, we saw there were a couple different ways of finding the class midpoints. You could either use the lower and upper to find the class midpoint, or if you know the class boundaries, you could take the average of the class boundaries. But since we can do it just based on the upper and lower endpoints of a class, let's just do that. So 0 to 4, what's the number halfway between 0 and 4? 2. So the first class midpoint is 2, and then you can keep doing that with every single class, or you know that if the class width is 5, everything always increases by 5. So the next one would be 5 larger, and then 5 larger again, and then 5 larger again. You just keep going up by 5. You could also say, okay, what's halfway between 5 and 9? It's 7. What's halfway between 10 and 14? It's 12. Okay. Well, it's the formula that I gave on the second page. It's lower plus upper divided by 2.
Right, but if you were writing out, if the thing was class midpoints, could you write 2 plus?
Oh no, you want the number. I want the number. Yep. Okay, and so the next one would be 5 up, so 22. 27, 32, and 37. Okay, so then for the class boundaries, so leave a little space actually for the first one. The second one, the first class ends at 4. The second class starts at 5, so we have to pick the number that's halfway between. What's the number halfway between 4 and 5? 4.5. And then if you want to do the rest of them, remember everything has to be separated by the class width. So the next one would be 5 up, 9.5. 5 up from that is 14.5. 5 up from that is 19.5. 24.5. 29.5. 34.5. 39.5. 39.5 is the last one because our table ends at 39, so we just go a little bit past that. So what would the very first class boundary be then?
Negative 0.5.
Negative 0.5, because they always have to be separated by a distance of 5. So if you put 0, there wouldn't be a distance of 5 between those two. Mm-hmm.
But it says years president lived.
Yep. It's still, if you're making the bar graph, your class boundaries have to have the same distance between them as the class width. So even though that isn't an actual value, it could assume you have to keep the same distance between the points. So you could do 4.5 minus 5 on your calculator, but it would be negative 0.5.
So kind of the class width drives a lot of the other.
Yes. Yes. And this actually, 21 and 22, this will be due on, I asked you to do that on one of the Excel, we won't do it in class, one of the Excel activities. And I'll talk more about the Excel activities before class ends today for what's due this weekend. Okay, histograms, section 2.3, and we did some of that yesterday. A histogram is a graph consisting of bars, and here's one important feature that I didn't really stress yesterday, that the bars have to be equal width. Now, we automatically do get equal width when we base everything on the class width. But later, we'll see some graphs where they don't necessarily have equal width. Then it's just like a bar graph then. It's not a histogram. And then the other important criteria is that they're adjacent to each other, which means there's no gaps between the bars. Now when you ask Excel first to create a histogram for you, it's going to give you a graph that has gaps between the bars, but in the videos I show you how to eliminate the gaps. The horizontal scale represents classes of quantitative data values. So the quantitative, that just means numerical, right? It makes sense to add or subtract or find an average. And the vertical scale represents frequencies. The heights of the bars correspond to the frequency values. Okay, and then, and I'm not calling it activity 3 anymore. I'm just calling it, I think there's a 2 point, I can't remember. I think there's a 2.2, a 2.3, and a 2.4. And again, I'll talk about that more at the end. Histograms give a good visual representation of the distribution of data. If the histogram is approximately bell-shaped, then the data have a normal distribution. So that is it for 2.2 and 2.3. 2.4, we're going to go ahead and just do this right now. There's not a group work that I'm doing for 2.4. So we'll go ahead through this section, and then we'll break to do the group work. And there should be also time built in to take an actual break, and then we'll get a little bit of a start on the 3.2. So 2.4 is all about the different kinds of graphs. And the title of the section is Graphs That Enlighten and Graphs That Deceive. And so the first thing they go through are graphs that enlighten. So graphs that really show good relationships. They help convey the data in a meaningful way. And the first type of graph the book talks about is a scatter plot. So a scatter plot or scatter diagram is a plot of paired XY quantitative data. So that just means numerical. So you couldn't use like a graph like this for hair color or political affiliation or something, because that's not a numerical value. Right? So both the X and the Y have to be numerical values. And yesterday, if you came early, I was talking about some of the homework problems. There was one that was like IQ and brain volume. Those were both numbers. So you could do a scatter plot for something like that. The horizontal axis is used for the first variable. The vertical axis is used for the second variable. The pattern of the plotted dots is often helpful in determining whether there is a correlation or relationship between the two variables. This issue is discussed at length when the topic of correlation is considered way at the end of the semester, section 10.2. So here what you're doing is just looking at a trend for the dots. So here this looks like it's probably body measurements, like what's your waist measurement? I'm assuming it must be in about centimeters there. And then arm C, I assume that's arm circumference. And so like this dot right here would represent one person whose waist is about 70 centimeters. It looks like it's about halfway between 60 and 80. And their arm circumference is, so 28 would be in the middle. I don't know, maybe about 28.5 centimeters. So each dot represents one person, and it gives you two pieces of information about that person. And then we look to see if there's a trend in the dots. So like if you sort of look at the cloud of dots, like if you had to draw an oval around the dots, is there a trend to that oval? Does it trend upward? Does it trend downward? This one trends upward. So what that's saying is as your waist increases, your arm circumference increases. Does that seem to make sense logically? Yeah. If you have a larger waist, you're probably going to have a larger arm. If you have a smaller waist, you're probably a smaller person. You have a smaller arm circumference. Okay, example 3. So again, here's a scatter plot, clusters in a gap, and this is for the pennies data. And so here on the x-axis, they have the weight of the pennies, and this is the same, I assume this is the same value that we had for the randomly selected pennies. It's just we didn't have the individual data here. We knew there were 18 pennies between 2.4 and 2.49, but we didn't know exactly what the values were for that, or what the years were. So here they've created the scatter plot. And so the ones that weighed less look like they're all after 1983, right? Because the years are higher than 1983. And the ones that weigh more, all of their weights or all of their years are before 1983, right? So it was the copper is heavier, right? And so we can definitely get some useful information out of this scatter plot as well. Time series graph. So it's a graph of time series data, which are quantitative data that have been collected at different points in time. So time series, this axis is always going to be measured in some unit of time. So this has to be a measure of time. It doesn't have to be years. Like you could follow the value of a particular stock. You could do it month by month, week by week, day by day. So you could have any unit of time on here, but the horizontal axis is always measured in time, and then it could be any other numerical value for the y-axis. So here it says the yearly high values of the Dow Jones Industrial Average for the New York Stock Exchange. And again, you can look at this to see a pattern. You can see there's a general upward trend although there are a couple places where it looks like something kind of funny went on in the market. And this, maybe if you've seen The Big Short, you know what this corresponds to, right? Has anybody seen that movie? So this was like the housing crash, right? Right in 2007. Yeah. Okay. Frequency polygons are similar to time series graphs. They use intervals, though, instead of one dot per year. So a frequency polygon is going to look kind of like that, dots connected with lines. But instead of, like, every dot here is 1 year. 80, 81, 82, 83, 84, 85. Every year gets its own dot. In a frequency polygon, though, it might do a 5-year period and pick the middle. So the graph is going to look the same. It's still going to be dots connected by lines. It's just not 1 dot per year, 1 dot per day. Dot plots. So a dot plot consists of a graph in which each data value is plotted as a point or dot along a horizontal scale of values. Dots representing equal values are stacked. So example 5 says IQ scores of low lead group. So I think they're talking about lead in water, right? So kind of relevant to the whole Michigan thing right now. So there was a group that they studied that had low levels in their water, and the graph we're probably not seeing is one that had high lead. So here it says the 5 stacked dots above the position at 76. So here's 70, and then it looks like there's, I'm going to zoom in a little bit here. So it looks like there's a gap where there would be 71, 72, 73, 74, 75, and so right here is 76. And we see 5 dots. So that just means there were 5 people that had IQ of 76 in that group. So the first time they came across 76 in the data, they put 1 dot. And then the next time they came across 76, they just put that dot right above the first dot. So it ends up being about like a bar graph. They're just using dots instead of bars. Okay, bar graphs. Uses bars of equal width to show the frequencies of categories of categorical data. And so notice this is the only time we've seen categorical data so far. So like this one, we could do a graph for like hair color, political affiliation, something like that. A vertical scale represents frequencies or relative frequencies. The horizontal scale identifies the different categories of the qualitative data. The bars may or may not be separated by small gaps, so we don't care about gaps here. A multiple bar graph has 2 or more sets of bars and is used to compare 2 or more data sets. So like here's an example of a multiple bar graph. So it's the median incomes of males and females in different years. So the data are from the U.S. Census Bureau, and the values for 2010 are projected at the time of the publication of this book. From this graph, we see that males consistently have much higher median incomes than females, that both males and females have steadily increasing incomes over time. Comparing the heights of the bars from left to right reveals that the ratios of incomes of males to females appear to be decreasing. When they say the ratios appear to be decreasing, it's like when you look at the first one, so they're saying the males are the darker bars and the females are the lighter bars. And so in the first one, the bar for males looks like it's more than twice as high as the bar for females. Same thing with the second bar. It looks like the bar for males is more than twice as high, but that's not the case in 2010. It's not twice as tall. It's still, there's obviously still a gap, but it's not quite as stark as it used to be. These almost look like the males are 3 times as high as the women, and it's a little less than twice as high by the time you get here. So this is a multiple bar graph. Every year has more than 1 bar. Okay. Pareto charts. When we want a bar graph to draw attention to the more important categories, we can use a Pareto chart, which is a bar graph for, again, categorical data. So not numerical data, with the added stipulation that the bars are arranged in descending order according to frequencies. So it always goes from highest to lowest, always Pareto chart. The horizontal scale, as before, identifies the different categories of qualitative or categorical data. The bars decrease in height from left to right. So here we see that these are the categories. They're definitely not numerical data. And it says what contributes most to happiness. So this was probably, they did a survey of people. And so family or partner was the most influential. Friends were next, then leisure, work, studies, music, and sports. Okay. Pie chart. So a pie chart is a graph that depicts categorical data as slices of a circle in which the size of each slice is proportional to the frequency counts for the category. So pie chart, always a circle that has wedges cut out of it. And it says it shows the same data as the Pareto chart. So we see here, it's still what contributes most to happiness, and that family partner takes up most of the pie. And then friends, and then work, studies, leisure, etc. Okay. Construction of a pie chart involves slicing up the circle into proper proportions that represent relative frequencies. For example, the category of friends counts for 13% of the total, so the slice representing friends should be 13% of the total area of the circle. I'm not going to ever have you make a pie chart by hand, so you don't need to worry about the degrees part of it. They're going to ask you lots of questions about pie charts versus Pareto charts on the homework. And so it says, these depict the same data in different ways, but the Pareto chart does a better job of showing the relative sizes. Like here, sometimes it's a little bit harder to tell how much bigger is this slice than that slice. It's just bars. I think it's just easier to think about, oh, this one looks like it's about twice as tall as that one. I don't know necessarily that the slice looks twice as big. Maybe it does. I don't know. But every time they ask you which is better, pie chart or Pareto chart, it's always Pareto charts.
So why do we see more pie charts?
I don't know why we see more pie charts, because you see them in the newspaper all the time. I don't know. I don't know if they think they're more visually appealing, I think.
Quicker?
Yeah, maybe.
Another question, does it, like, a pie chart has to have 100 add
Yes.
Is it Pareto chart, does that have the same parameters? 'Cause it looks
Yes.
like you could kind of fudge on that.
Nope, they both have to add to 100%.
But maybe it's just a graphic thing.
Mm-hmm.
None of the columns are marked with percentage.
Right, they're not. And
Is that a rule or just a thing?
it's better to display so you can check, but again, a lot of things won't. In the Excel activity, I do ask you to, especially in the pie chart, either display the percentage or the frequency. I don't care which one, but so you can tell, because it is, like I said, it's hard to look at this and visualize which is which, or what are the relationships between the categories. So this is the book's suggestion. So it says, graphics expert Edwin Tufte makes the following suggestion: never use pie charts because they waste ink on components that are not data, and they lack an appropriate scale. That's just his graphic expert's advice. Okay, those were graphs that enlighten, and now graphs that deceive. So it says some graphs deceive because they contain errors, and some deceive because they're technically correct but misleading. It is important to develop the ability to recognize deceptive graphs. Here we present two of the ways in which graphs are commonly used to deceive. Example 13, non-zero axis. So when you first look at this graph, you think, oh my gosh, whatever they're measuring, Toyota Camry. So this is highway fuel consumption. So you'd think, oh my gosh, the Civic uses way more gas than the other two types of cars. But notice that they're starting the graph at 30, right? So all of them get more than 30 miles per gallon. So it's not zero at the bottom. Here is the graph when they do put zero at the bottom. So you can see there are differences, but it doesn't look like the Honda Civic is like 4 times worse than the Camry, right? You can see there are differences, but they're just, so this was kind of maybe deliberate distortion sort of thing. They do have the heights of the bars at the right numbers, but they're just misleading when you look at the proportions of the heights. So you should always start at a non-zero axis. But again, you will always see graphs that don't have zero at the bottom. I see those, especially like if you're talking about, oh, like CEO salaries or something. They're not going to start at zero and then go to 4 million, right? They're going to start at 2 million or 3 million or something and then show the different salaries. Pictographs, and again, like USA Today is, I think, probably one of the most common sources of like these pictographs. I think they use graphs like that all the time. They look clever. You can tell exactly just by looking at the graph. Obviously, this data has to do with airplanes, right? So they can convey some things, but again, it's a little bit misleading. So drawings of objects called pictographs are often misleading. Data that are one-dimensional in nature, such as budget amounts. So one dimension means they're only showing one thing. Like they're only showing what the budget was. They're only measuring one variable. Here, like what they're basing it on is the area of the drawing. Like this, like, you know, if it was a rectangle, length times width or whatever, this is a weird shape, so you'd have to use some weird formula to figure out what the area is or just approximate. But it's a lot harder to try to show one number in like this two-dimensional thing. Although a bar is two-dimensional, but the widths of the bars are the same in both of them. So you can kind of ignore the width doesn't really account for anything. It's only the height. Since the widths are the same, you only have to compare the heights. You only compare one thing. So it says, yeah, they're data that are one-dimensional in nature are often depicted with two-dimensional objects such as dollar bills, if it's money, or three-dimensional objects such as stacks of coins, homes, or barrels, like if they're talking about oil or whatever. By using pictographs, artists can create false impressions that grossly distort differences by using these simple principles of basic geometry. When you double each side of the square, the area doesn't double. It increases by a factor of 4. So like, think of if we had a square that was just 1 unit on each side, and area is length times width, then the area would just be 1 square unit, whatever the unit is. But if I double that, so I make it 2, so here was the original, and I just make each side twice as long, right? So I double the side length, but now the area is 2 times 2, or 4 square units. So making something twice as big, like one dimension or both dimensions of it twice as big, makes the area it encloses 4 times as much. So here, it's just a lot easier to tell from a bar graph. Yeah, this one looks like it's about twice as tall as the first one. For me, the airplane, it looks twice as big, maybe, right? It looks like if I take this length, yeah, that would be like 2 of those airplanes kind of would fit in here. But it really, the area is increased by 4. It's okay if you are not totally following this. Just keep in mind pictographs are not a good way to display graphs. Okay. Oh, that is it.